Welcome to another video on smart architectural programming, and in today's video we'll be focusing on another blind 75 problem, in particular the combination sum problem from the blind 75 list of questions. At this point, again, I would like to remind you that the blind 75 list of questions from LeetCode are one of the most important tools that you need to go over, understand, and practice on if you want to pass your coding interviews, because these stem from the basic concepts that are going to be tested over and over again in most coding interviews. So with that, let's dive into this combination sum problem. So if you have some experience with statistics, you might be familiar with the combination term. But if you aren't familiar with the term statistics, you might be unaware of that term. So basically, generally what you need to remember to understand this particular problem is that we have a target number, whatever that may be. And in this I'm just going to pick up one from here, which is 9. So we have a target number, right? And I'm trying to explain combinations in the most easiest way for people who are not familiar with the combinations terms if you haven't taken high school or graduate level statistics, right? So based on that, we're given a list of numbers, right? So our target number is 9, and we're given a list of numbers, which is basically, let's see, 2, 5, 6, 9, right? So we have numbers 2, 5, 6, and 9. So given these numbers, we need to create combinations of these numbers so that these combinations equal to the number 9, right? So that is basically what we need to do. So what do these combinations look like? So basically, these combinations would look like something. So we need to get 9, right? So a combination is, for example, 2, 2, 5, right? Collectively, this becomes is equals to 9. So that's one combination. But if we do something like, let's say, 5, 2, 2, that also comes over to 9. But that's not a combination. This is a permutation, because it's just reordering the values here into in another form. So that is not what we need to do. So we don't need to create permutations. We need to create combinations. So don't reorder letters. So if we have 2 to 5, any combination that has an arrangement with 2 to 5 is unacceptable. That's not the value that we can use as a combination. So based on that understanding, we need to create an algorithm that basically runs this and gives us a value that we can use. So to be honest here, like, it's a relatively tricky aspect to cater to, right? So if we brute force this method, like if we use brute force method to solve this, we can potentially basically, so if we have, let's say, values here 2, 5, 6, and 9, right? Given these values here, if we will brute force these values, all of these values, right? If we use the brute force method, it would include something like this, right? We'll add different combinations of these values from each of these branches and try to create combinations which have the value which sum up to 9, right? So the brute force method would be simply, let's start with 2. So we start with 2 and then we write 2 and 2, right? Right? So that's 2, 2, 4. Or rather, let's I think a different way to explain this would be, so we do different combinations of 2 here, right? So 2 and 5 here. At the same time, here could be 5 and 2, right? So that makes it so that the brute force method is a non-viable method to solve this problem. It's a completely non-viable method to solve this particular problem. So how would we go about solving this problem then, right? The 2, 5, 6, 9 are our digits, right? So let's start that, right? So first we need to build a decision tree, right? So how would this decision tree work, right? So we have, on one side, we select the first letter, which is 2. And on the second side, we select the value empty, right? So we have not decided on any value here, right? So based on that, we'll start making decision trees further down 2 as well. So on one side, we'll add another 2 here, right? On the other side, we won't add anything, right? But we'll start adding other numbers, but that we can't add anything on the other side at the moment, right? We'll just go on this side for now, right? So we have 2 and 2, that's 4. So that's still not the number, but it seems like we're going the right way, right? Then we create another decision tree here. We add another 2 here, 2, 4, 6, right? Again, that doesn't seem to, these sides are where we stop at just 1 digit. So here we just stop at 2, 2, and here we just stop at 2, 2, 2, right? So basically, based on that, we're just moving on the left side. So 2, 4, 6. Then if we go one step down here, we get 8, right? So, and then we go one step down there, we get 10. So it seems 2 is not going to give us the combinations that we need here, right? So that branch seems useless. Similarly, here it's we start here. Give me a second. So here, let me remove this 2 here. This was more than it should be here. So we just add a single 2, right? So here we start adding different combinations with 2. So we have 2, 6, 5, 9, right? 2, 5, 6, 9, right? So we try 5 here next, right? 2, 5 is 7, right? Then we have an option of maintaining 2, 5, and on the other side, maintaining 2, 5. On the other side, we can just add a new value. So decision trees like these would be branching out further down the line, and as these branch out more and more, we'll be able to create a scenario where we can find unique combinations of these values, right? In this case, we can't use a digit more than once in different orders, because just using 2 is one branch, the other branch is using 2 and 5, so on and so forth, right? So it makes us safe from any permutation that might creep into our algorithm as we're working here. So once we're done with 2, we can select any other number here, let's say 5, and just try to do all of this that we're doing here with 2. Let me use a color here. So all we did here with 2 is going to be done here with 5, and we're going to create branches to do that and find permutations of 5 that reach out, combinations of 5 that reach out to become the value, target value ultimately. So that is the logic behind this particular problem. So based on that, we have this solution here that we have coded. So how does this solution work, right? What's the logic behind it? So first, we need to sort the input because it helps us in optimization by allowing us early termination recursion when the sum exceeds the target. And you can see that that particular aspect to this problem where we are sorting the input here in our code as well. As you can see, we sort the values and then move forward towards our next solution. So then we need to use recursive backtracking, which is basically start with an empty list for the current combination. At each step, either include the current number, allowing repeated use, or move to the next number, as we were showing in that decision tree that we worked with. If the current combination sums equals to the target, add it to the results. If the sum exceeds the target, stop exploring further on that particular tract of the decision tree, right? And base cases are if the sum matches the target, add the current path to the results, and if sum exceeds target, return basically. So that is how we're doing. So you'll notice that the recursive function, we have the start value, the index, which is the current number to consider, prevents duplicates, and ensures combinations are unique. You can see the start value here in the function that's going in, and that's what it's doing, and that's the purpose of the start value here, is to make sure that the index of the current number and prevents duplication and ensures each combination is unique. Then we have the target number, and then we have the path. The target number remains remaining target after considering numbers in the current path and current combination being explored basically. So target number in this case, it's a slightly different than what I mentioned in the explanation here. So if you have a target number and we're going down one branch path, right? So if let's say our target number is 9 here, right? And we go to 2 here. So our target number, new target number would be 7, right? Similarly, if we go down here, our new target number would be 5, right? We reduce the target number as we're moving down the decision tree. That's what the target number is doing in the code here, as you can see. Similarly, the path is the current combination being explored. So the path, as I mentioned here, 2, 2 is the path, and this becomes our entire path, right, on the decision tree, so on and so forth. So the path is the amount of combination we're taking on the decision tree. We can't visualize that in code, but we can visualize that within graphics to understand exactly what's happening. So Based on that, let's move on to the next aspect of the code, which is that we have a base case to get out of recursion. So target, if is equal to 0, if target is equal to 0, the path forms a valid combination, so we append it to the results. If the target is less than 0, we stop further exploration, basically. Similarly, we iterate and recurse, basically loop through the numbers from the start index to ensure no duplicates and allow reuse of the current number. The time complexity of this particular problem is O(T)(T)(2)T over M, which is basically something like this. Let me show you here. So target time complexity is something like this for this problem. And basically what this, to break this down, what you need to understand is that T is the target and M is the smallest number in the array. This is due to the fact that we're exploring all possible combinations. And space complexity is basically which depends on the depth of the recursion tree, is OT over M, right? Again, these are the values of these particular of this particular algorithm. So with that, let's run this code and see if it works. As you can see, all 3 cases here were accepted, and then when we submit this case, all 21 cases were accepted as well. That is how you solve the combination sum LeetCode problem from the blind 75 LeetCode list of questions. And with that, I'm going to sign off and see you on our next video. Thank you.